we are looking at what are called coordinate proofs. Okay, and coordinate proofs are sort of like paragraph proofs. They're more like paragraph proofs than they are two-column proofs. But a coordinate proof really, instead of writing sentences, we're showing work. So it's going to be, it would be sort of a combination of sentences and just showing our work. Because what we're doing is we're proving stuff on a coordinate plane, which means we are going to deal with distance formula and midpoint and maybe area and perimeter, right? Those sorts of things that we can do on a coordinate plane. That's what we're trying to prove here today. All right, so you see our one word there, coordinate proof involves placing geometric figures in a coordinate plane. So that's the first thing that we're going to look at here. And you see part of it is just how can we place this figure in the coordinate plane when we don't know the length or the width, right? Here they just say, I want a rectangle in the coordinate plane. They don't have a length of 8 and a height of 4 or whatever, right? They don't give us any more information. So we just need to create that rectangle someplace. And if we were in class together, I would have you on your own page draw a rectangle where you think would be a good spot to put it. And I always get people that are, just putting a rectangle here or maybe here. I've seen some people do a rectangle like that for some reason. But what's going to work best for us, and because remember, we're going to have to do midpoint, we're going to have to do distance formula, we're going to have to do these equations with this stuff. We want as many zeros as possible. So we want as many zeros as possible in our coordinates, which is why you see down here, right? The way that they located that on the coordinate plane. They put one of their vertices at 0, 0, and they had everything else being positive. That way we don't have to deal with negatives. And we've got a bunch of zeros, right? Out of the 8 coordinates here, the X and Y coordinates, 4 of them are 0, which allows us to do some calculations a little bit easier when we start looking at it later on. So that's what we want to do. We want to put a vertex at 0, and we want to have sides on 0 as well on the axes if we can. So we're going to put that rectangle in, right? You don't have to use H and K. We just don't know the length and we don't know the width. So we have to put some variable there. It could be X and Y, it could be A and B, doesn't matter. We just have to have something. And we know that it's a rectangle. So our length and our width are going to be different. Our length and our width are going to be different, right? So we have to use different variables for those two. If they were the same, if it was a square, then I would have the same variable, right? If I'm looking at a square, let me do it off to the side here. If I'm looking at a square where I know every side's going to be the same, maybe I call this one X comma 0, right? Because I'm going some distance there. I don't know what it is. But then if I'm going the same distance up, this point would have to be 0 comma X then, because it's the same distance, right? Which would mean my 4th vertex here would have to be XX, because now I'm going over X, I'm going up X. That gives me that other point. So part of this is just being able to put the figure on the coordinate plane. You see the triangle, the scalene triangle that they have here. All our side lengths are different. So we can't have the same variable. They used a D for the length. They used F comma G to put another point up there. That's just all different variables because they're all different lengths. So we can't have the same variable there, okay? So that's part of it. Let's say that I wanted to do, well, we'll come back to that because there's a problem that deals with it later. All right, as we're going, if you have questions, either chime in or type them in the chat, completely okay. Let me pull up another picture here. All right, so what we're going to look at here, this is the one type of coordinate proof that we're going to see. And they're not actually asking you to prove it. They're just saying to write a plan for it. So what would we have to do? And they don't want you to do it. They just want what would we do? So if we look at this, it's given that GJ bisects OGH. So if we see that, oops, sorry. Still getting used to this. First day I've used this fancy stuff here. So it was given, look at that, I can zoom in. It was given that these two, or that GJ is the bisector. And if it's the bisector of the angle, that means that these two angles are congruent. So we would say that those two angles are congruent because it's the definition of an angle bisector. We could use reflexive property, GJ, to say that that side is congruent. And then we need another piece of information, right? We either need another angle. We would need to know that our two angles would be congruent, or we would need to know that our two sides, the left and the right, are congruent. We can't do anything with angles on the coordinate plane because we don't know how to do that. We don't have a way of finding those angles yet. But we do have a way to show that these sides are congruent, right? We do have a way to show that. Distance formula, right? That's why we did the warm-up. That's why we did distance formula, is because we would then use distance formula to find that OG and HG are going to be congruent. So if we use that distance formula, that proves to us, oh, I was hopeful that that would shrink too. It didn't shrink. Oh, well. That proves to us that GJO is congruent to GJH then, right? By side, angle, side. Okay. So that's one sort of thing that we're going to have to look at there. Let's look at another one. This one's going to use CPCTC a little bit in this one. And I showed you the solution so that you can kind of see what they're looking at in terms of how they're doing it. Let me look at the chat here. Maybe linear pair for an angle instead. We could have used linear pair. That linear pair would have shown that the two angles add up to 180. It doesn't necessarily mean that they are congruent. We would have to say that they were right angles, which would mean we would have to find the slopes and use, the perpendicular lines theorem to show that they're perpendicular, which means they're right angles, which means they're congruent. It's going to be a whole lot easier just to use that distance formula. But that's a good idea, right? Just to look at those angles because we could have used ASA there. All right, so looking at this one, we're writing a plan to prove that SO bisects PSR. Okay, so now we're kind of going backwards on the last one. Last one, they gave us that was an angle bisector. This time, we have to prove it. To be able to prove it, we're proving triangles congruent. So we're going to prove these two triangles congruent, the left and the right. We still have reflexive property there. We can count that these are the same, right? So PO and RO are congruent. And then they're going to say to use SSS. Again, this, like I was just talking about, we could technically prove that angle O, SOR and SOP are congruent because they're right angles, but we would have to go through the lines are perpendicular. That means they're right angles. Because they're right angles, they're congruent. It takes a little bit more. Instead, what they're going to tell us to do is to use that SSS. We already have two pairs of sides. We would just need distance formula to get the third pair of sides. Once we have that third pair of sides congruent, right? All three pairs of sides congruent, SSS, the triangles are congruent. Now we can use CPCTC, right? And they have it in here. They just don't have it abbreviated, CPCTC. My picture's in the way on my screen, so I can't underline the C. Anyway, CPCTC, we can say now that these two angles are congruent because of corresponding parts, corresponding triangles of congruent triangles. And that would prove then, because those two angles are congruent, that would prove that SO has to be a bisector. Okay, so we're working through what we have. We're just using distance formula a little bit more than we would if we didn't have the coordinate plane, right? So it's the same ideas as what we've seen with our proofs. You're still going to use CPCTC. You're still going to be doing all that. We're just going to see it on the coordinate, so we have to use that distance formula. One thing to point out here is notice how they put this figure now. Okay, they put this figure so that the height, so that the y-axis cuts straight down the middle. Okay, this would be instead of, let's see if I can draw it here. This would be instead of drawing the triangle out here, right? Because out here, I've got a 0, 0, I've got something comma 0, but that's it in terms of my zeros. And the whole goal, remember, is to try to get as many zeros as you can with this figure, because that's going to help with what we're going to do next. So that's why they slid it over. Yes, they have a negative there, but that allows us, if let's say we were trying to prove the two halves congruent, that allows us to say, all right, this distance is h, this distance is h. We know those are congruent, right? We can see that. And you know, it can be a little confusing with the letters here, and when do we do negative, when do we do positive, different letters, same letters, all of that. It all depends on the type of figure they're telling you to use, right? If they're telling you to use an equilateral triangle, well, that's this picture here. This is an equilateral triangle, right? If they're telling us to use a scalene, that's going to be different. If they're telling us a rectangle, that's going to be different. So I can't say for sure, you know, you always have to do this, because it's going to depend on what figure we have. Okay, let's look at one more here. We'll look at this, and then we'll look at one last thing, okay, and then we'll be good. So this one, we are writing a coordinate proof. And remember, coordinate proof is just showing the work, right? It's showing the work and showing what you did to be able to prove it. So it's not a 2-column. We're not writing out steps. So the given here, the only given that we have is that they are the coordinates that are shown. And they gave us the letters this time. Okay, they gave us the letters. We have to use the letters now instead of coordinates to be able to prove this. So again, we're trying to prove that OTU is congruent to UVO. We can still use reflexive, even though we are in a coordinate plane now. We can use reflexive. OU and OU are the same. OUUO are the same. So that's reflexive. So we would write that down. If we were writing out a coordinate proof, we would say, you know, OU is congruent to UO by reflexive, right? We would have that, POC. We would have that written down. And then we would have to get the other sides. And really, when you're looking at a coordinate proof, it's all about sides. It's about the lengths. So it's going to be side, side, side that we're using here. We're just going to have to use distance formula to find those. So if we use distance formula for the top and the bottom, for TU and OV, okay, let's do the bottom first. If I'm going to use distance formula, I'm still going to do it just like we did in the warm-up, only now I've got an H to throw in there. So that would be the I keep saying absolute value, the square root of H minus 0 squared, and then 0 minus 0 squared. Well, I simplify this all out. I'm looking at the square root of H squared. So that distance is just H, which we know. We can look at that, right? We don't need distance formula to tell us that distance is H. I just wanted to show you that the distance formula still works when we have letters in it. Okay, it still works when we have letters. So we are going to, hold on, let me erase a little bit here. And then I'm going to find the distance on the top. Now the distance on the top, we really don't need to use distance formula either, because this point T is over M, and then this is M plus H. So we know that distance is H. So really, we could just look at that and tell the distance. So the top and the bottom are both H. We know those are congruent. So we're good there, right? So we know those are congruent. If you have questions, make sure you're chiming in or write in the chat. So we know those are congruent by looking, by counting. That leaves us with that third side. And now we have to use distance formula. Okay, we have to with our letters. Let's do TO here. That's going to be the square root, subtract my x's, so m minus 0 squared plus k minus 0 squared. That's going to give me m squared plus k squared, the square root of that. Now, I can't go any further. I can't combine. I don't know what m squared and k squared are, and when I combine them, what that's going to be. I'm going to leave it just like that. I'm going to simplify as much as I can, and then I'm going to leave it just like that. That's TO is equal to that. Okay, so, but now I got to do UV and see if UV ends up being the same. So for UV, if I subtract my x's, I'm going to do m plus h minus h, right? That's subtracting my two x values. One was m plus h, one was h. And then the other one is still going to be k minus 0. So when I simplify that, the h's are going to cancel in there, right? Those h's are going to cancel. I'm just left with m squared plus k squared. Well, it's the same thing, right? It's the same thing. So even though I don't have a number value for it, I know that those two lengths are the same because distance formula left me with the same thing, the same letters, the same everything. So because those are the same, I can say that they are congruent, which means we have side, side, side for that. Okay. Any questions that you have about that coordinate plane or coordinate proof? Because everything that I've written here, that is the coordinate proof, showing the work, right? Showing that these two things are equal to each other. That is the coordinate proof.
So literally for a coordinate proof, you just have to show work?
You just got to show work. Yeah, and we should probably write, you know, the one thing that we can just tell by looking is by, you know, reflexive property. Let's write that down, but the rest of it, yeah, is work. Let's see. It says, how did you get the negative h or the minus h again? So here, I'm going to use a different color. The m plus h is that x value. And then this h is this x value. And when I'm doing distance formula, I'm subtracting my two x values. So I took the m plus h and then minus that other h. That's how I got that. Excuse me.
Do we ever get like parallel sides?
You could get parallel sides. Yeah, if they gave you parallel sides, then for sure we're going to use AIA. Yeah, but we probably won't see that a lot in this type of proof. Yeah. Any other questions about it? All right. I want to point out one more thing here. Let's say that we know it's an isosceles right triangle. So if it's an isosceles right triangle, and I want to prove that the midpoint of the hypotenuse, something about the midpoint of the hypotenuse, okay? So I want an isosceles right triangle. I'm going to put that right angle in the origin. I know that it has to be isosceles here. So I know my distance has to be the same over as it is up. But again, I'm dealing with the midpoint of my hypotenuse here. So if I were to label this point as, let's say, x comma 0, well, this midpoint, well, then this would be 0 comma x, right? Because it's over the same amount that it's up. This midpoint then, if I use midpoint formula, that's add the two x's and divide by 2, add the two y's, divide by 2. That midpoint would end up being x divided by 2 and x divided by 2. And I've got fractions in there. And what's going to happen is they're going to say, all right, now we want to find the distance between that midpoint and the origin. And I don't want to have to do distance formula with fractions and variables and all of that. So we want to think of a different way that we could label these coordinates so that my midpoint doesn't end up being a fraction. So if we think about this, any ideas on how we could do that so that my midpoint isn't a fraction? So I know it's going to be something 0 and it's going to be 0 something here. If I'm going to have to find the midpoint, okay, if I'm looking for the midpoint, that means I have to divide it by 2. And if you look at your x values, if I'm finding that x value of my midpoint, right, I'm going to add 0 plus something, and then I'm going to have to divide it by 2. So instead of just putting an x there, we're making these up, right? We're deciding what these lengths are going to be, what variables are going to be. We can call that 2x. Because now if I'm finding the midpoint, I'm adding 0 plus 2x, which is 2x, and I'm dividing it by 2. That means my midpoint here is just x. That gives us a better way to do some calculations rather than having to do a fraction on it. And then if it's 2x to the side, it's got to be 2x up as well. So that would be 2x. That midpoint would just be x comma x. That's going to allow us, if, like I said, we have to do this distance formula, I don't have to worry about fractions. I've got that number there, right? Or just that letter, and I don't have to worry about the fraction, the divide by 2. This is probably the high end of what they are going to ask you to be able to set this up with a multiple of 2 so that you can cut it in half, right? That's forward thinking. That's thinking, all right, this is what I'm going to have to do. So let's make it easier on myself by doubling it, by making it a 2x. So when I do have to cut it in half, it's just x and not a fraction, okay? I know that can be a tricky concept sometimes, but hopefully that sort of makes sense to you there. You might see it in the homework, you might not. We'll see what they have. All right, any questions on any of our coordinate proof stuff here?
Will there be a question like that on the test?
If there is, they would walk you through it. They might give you the 2x and the 2x. I'll be more specific tomorrow on what's on the test. I got to look it over again and make sure everything's good on there. But I don't think it would be like a do-it-yourself at all. No.
Okay.
Anything else? Any other questions that we have? No?